All right. Sorry? Oh, this? Oh, it's a video. I'm live streaming it to YouTube. Yeah. All right. So welcome, guys. Thank you for coming. As you know, yesterday Giri went over a pretty hard topic, which was computational geometry. It was also a problem in the 2021 North America qualifier, and I'll tell you right now how many people solved it. So 81 people tried to solve it, and only 22 succeeded. So that's a 27% success rate, which is pretty low. So it definitely shows you that this is not an easy problem. It's not a trivial problem. So first, I'm going to go over what the problem is telling us or what it's asking from us. But before I do that, let me ask Demba and David, since they were there yesterday, what exactly are they asking from us? Let's see if you guys remember.
Basically, we got an asteroid. No.
You have my black marker?
I do.
Okay, yeah.
You want me to throw it?
Yeah.
Nice.
All right, go.
So we got a spaceship that conveniently is just a particle. Don't think too much about that. And it's trying to reach a base station, which is in some area in 3D space. So it's trying to reach there, but at the same time, there could be at least 1, 2, 3 asteroids in an asteroid field that it has to cross through. These asteroid fields and the spaceship have a direction they're going in, right? And so, the asteroid is clearly going in the direction of the base, but the asteroids are going wherever they want to go. The asteroids have a direction. They have a speed. No, they don't have a speed, right?
They do.
They have a speed.
Oh wait, no, yeah, their speed is unknown, but they are traveling in a direction.
Okay, they're traveling.
Do you have the starting position?
Yeah.
Yeah.
The starting position of the center of mass.
We got the starting position of the asteroids and of the spaceship. So then you want to know if it's clear for the spaceship to get to the base station without hitting an asteroid. And I'll let you explain how that.
Right. Demba, is there anything you want to add to that?
No, he said it very well. It's just an asteroid trying to get to the base station without any collision.
The spaceship.
Yeah.
The spaceship trying to get
And the asteroids have started.
Yeah. So just now to add a visual representation, let's call this your base. You have a spaceship over here. And to give some more detail on what the problem really says, there's some of it's nonsense, but you're running away from a couple of enemies. So you want to go from your spaceship to your base as fast as possible, and you only have enough gas for one boost. From right there, it tells you that you want to take the straightest line possible, because it tells you that you want to get away from your enemies as fast as possible. Therefore, the fastest path between any 2 points is a straight line. And since you only have enough gas for one boost of your engines or whatever, that also tells you that you can't go here and then boost again to go there.
Our initial speed is 0.
Your initial speed is unknown. Even though you have enough gas for one boost, you don't know how much that's going to push you. Yeah. And of course, the hard part is that there is a certain amount of asteroids between the base and your spaceship. These asteroids, give me a sec. These asteroids, they're rotating at an unknown speed. Their speed itself is unknown, but what you do know is where they start at and their direction. And they also give you the convex hull of that asteroid. Yeah.
I just wanted to add something to this question. You don't know the speed, right? But you do know that if you get that boost without any collision, you're going to get to the base station.
Yeah.
So you don't have to worry.
So the boost will always get you to
The boost, yes. You're always going to aim straight to your base. So the boost will for sure take you to your base if you don't collide with any other asteroids.
So in this scenario we have, there's no momentum, there's nothing like that.
You don't have to worry about that. Yeah, exactly. We're going to break down the problem, and then you see exactly why this is computational geometry and what it's really asking us. But so far, everyone understands the problem, right? We're all on the same page? Cool. All right. So let's go over some basics for vector algebra or whatever, linear algebra, I guess. So let's say we're given 2 points. If we're given any 2 points, we can form a vector. Does anyone know how we can do this? With any 2 points, how we can form a vector? Guys? But the both of you should know. Yeah, so you want to do the difference within their coordinates. So if I have point P and point Q in some 3D space, if I want to do a vector from P to Q, I can just do the subtraction, then we'll present a vector like that. In other words, it will be something like this: x2 minus x1, y2 minus y1, z2 minus z1. All right. So this is, like it says right here, just the basics and some things we should keep in mind for the remainder of this lecture. All right, how about a magnitude of a vector? Anyone?
I'm pretty sure you add the squares of all 3 of them and you can take square root.
Exactly, yeah. So now that we have our PQ vector, you want to find our magnitude, which we can denote using 2 lines. We can also denote it by just using 1 line. That's going to be exactly what you said. It's going to be the square root of the square of every element, the sum of that. So it's be x squared plus y squared plus z squared. So the square root of the sum of the product of each element. And the product, I mean like product of the first element times the first element itself.
And question, what's the difference between the single bracket and the dual brackets for?
Yeah, there's no real difference, but I think this is just the same thing as it's still the magnitude, but I believe it's just normalized. But I don't really think it serves any difference.
Thank you.
Yeah. Now the next thing that we want to go over is dot product. Anyone remembers this one?
I times j equals k, all that stuff.
Yeah, oh yeah. So if you want to look at it like that way, yeah. Or you can also just say, here, I'll write it out. Let's say we have u times v. Okay. It's x1, x2 plus y1, y2 plus z1, z2. So it's each element and each vector, the product of each element in each vector and the sum of that. So x1, x2 plus y1, y2 plus z1, z2. This is also equal to something else. It's equal to the magnitude of the u vector times the magnitude of the v vector times the cosine of the angle between them. That's another way of writing the dot product. These 2 things are actually exactly equal to each other. It might be like pretty difficult to see, but do you guys want me to get into showing why this is equal to that? Or do you just want me to ignore it?
It's fine for now.
It's fine for now? Okay. General consensus, that's 1. We need someone else. David also thinks it's fine.
What is the latter part? The magnitude times the cosine of
Theta.
theta?
Magnitude of u times the magnitude of v times the cosine of theta, where theta
The angle between the vectors,
yeah, angle between 2 vectors, exactly. And I know that's an ugly theta, so I apologize. I'll rewrite it. There we go. It's a little bit better. And this is actually exactly how we prove this part, by looking at their basis vectors or their components of this vectors. All right, so, but we are going to skip that part because of general consensus, democracy, I guess. Now we're just going to cross product. Anyone want to tell me what cross product is? Does anyone remember? I will give you a little hint. Cross product and dot product, pretty much exactly the same. There's just one difference.
I think it's the entry K thing. I think I'm mixing that.
Huh?
I think like when you multiply, let's say you were to take x1 times
Yeah, it's something different like that. It's not exactly this. It's actually much messier. Yeah, so that's something good that I was going to bring up. But dot product, it's a scalar. Cross product is a vector. And like he pointed out, it's much messier than this. But if we look at this part, the cross product is pretty much like the exact same thing like I mentioned. But instead of cosine, it's going to be sine. Huh? Oh yeah, you're right. Thank you. Appreciate it. Let's be y1, z2. What is z1, y2? And since this is a vector, and I'm writing it out as a row vector right here, we usually represent vectors in columns. So I'm just going to denote the transpose there. So you guys know that this is supposed to be represented as a column like this one. Now, like I said, this is also just equal to the magnitude of u times the magnitude of v times the sine of the angle between those two. Like David pointed out, this is a vector. Now, what does that vector represent? Let's say we just have a 2D vectors. What would this be? You can also think of it as just 3D, but just in the x and y.
Like, it's basically sort of like right-hand rule.
Yep,
Yeah.
exactly. So this vector is going to be perpendicular to these two. That's why if you do the right-hand rule, your thumb is going to be that cross product, and it's going to be the perpendicular one. So you're trying to put these two fingers to whatever these two vectors are. And I guess I can do it like that. Or I can also do it the other way, and I'm pointing down. So the direction is either positive or negative. And the magnitude of that vector is the area of the parallelogram that these two vectors make. That's not really something important for this problem, but that's just another principle or something else that cross product tells you. Any questions for now?
So that's the formula for that cross product, right?
Yeah, for 3D.
For 3D.
Throw a three-dimensional vector. For 2D, it's different. For 4D, it's different.
Cross product gives you like a magnitude and a direction, right?
Exactly, so another vector.
So another
Actually, since it has direction, I need to do n hat, where n hat represents the direction of that vector.
That's the difference with the dot product. It doesn't give you that.
The dot product just gives you a scalar, exactly.
But they both give you different vectors, right? Like the magnitude of the two vectors are going to be different.
Yeah, I believe they are going to be different. If you just look at it, you can also just see how this one has cosine and sine. So if we just ignore the direction, the values are for sure going to be different.
But what did they tell you? Like, for instance, those two, what would be like cross? Like, what
Here?
would be, no, like the example that you be in the tear. How would the cross product vector look like, and how would that?
Say this is a cross product vector, it would be like that.
Okay, and how about the other one?
The dot product is just going to be scalar. There's no vector.
So it's going to give you a magnitude.
It's just going to give you a magnitude, sure.
But the other one has a direction.
Yeah, exactly. All right, I'm not totally sure about this, so I didn't say it, but I believe that the value that this gives you represents how parallel they are to each other or something. I'm not sure. But this value does represent something else. I didn't really look or didn't really search up, but it does represent something, of course. Everything always has a meaning. So this is the basics I want to show you guys, or at least bring up before we really get into the problem. Is everyone so far okay with this? Or is there anything you guys want me to clarify or to say out loud in case you can't see it? Dot products.
Yeah.
Does it represent anything?
I saw that like when if it's at a right angle, it's 0. If it's
Yeah.
at 0, it's
So that's something else I was also going to mention. Notice how it's cosine and sine. If this angle is 0, what would cosine of 0 be?
1.
Just 1. If it's cosine of 90, what would it be? So that's be pretty big later on in the problem. Cosine of 90 is 0. So let's just remember that. I'm glad you brought it up already. But let's just keep that in mind. All right, so am I good to erase this? Everyone wrote it down?
Yeah, one question. What is that T at the of the parentheses, the exponent?
Transpose. So since this is a vector, we commonly represent vectors as column vectors.
Okay, so it shows that.
But since I did it in a row, I just did the transpose. Because the transpose of a row is a column vector. Yeah, because transpose this, you get 1, 2, 3, 4. And if you transpose this, you get that. Cool. All right, everyone's good? Yeah? All right, Dembo, you good? All right, and that's another thumbs up. All right, so we just went over the basics. That's pretty much all we're really going to need, I believe, for this problem. Everything else is just going to build off of what we just discussed. All right, so what now, right? What do we want to do with this information? Let me ask you guys, now that you know what the problem is asking us and you know what we just went over, is there any connections you guys can make? Sure, let's give it one more minute and then you can answer.
Well, we're trying to get to the spaceship without running to asteroids. And we have a point with undetermined speed and direction as a spaceship. The same thing for the asteroids.
We know which direction.
We know direction of the
Yeah.
spaceship?
We have
Yeah,
the
we
direction.
do know the direction.
Okay, let's go.
And of all the
Because since we know where the spaceship starts and we know where its base is, we can know like what direction it's going to take to go from one point to the other.
So that's like the first thing we do is we have to calculate.
Yeah, that's actually is the first thing. We have to calculate the direction of the spaceship by doing the difference of those 2 points, which was the first thing that we had up here. Yeah.
And the issue right now is we're trying to avoid the asteroids.
Exactly. Yeah.
We'll return whether we can go or we
Yeah.
should.
Or should, okay.
So if we for sure cannot avoid it, then we know we're screwed and we say surrender. That's what we output. But if we could avoid it, we say go.
You also know the direction of the asteroids, right?
Yeah, we know directions of the asteroids.
You also know the direction of the station.
We know the position of the center of mass of an asteroid, and we know the direction of that center of mass. All right, Dembo, you want to say it now?
Yeah, sure. So we know the direction of the spaceship. We also know the direction of all the asteroids, right? So the only way, but we have no knowledge of any speed. So the only way we can make it to the base is if there is no intersection between the asteroids and the spaceship. So that's what we have to find.
Yeah.
They intersect at that point.
So now, I'll draw that back. We have base. Go spaceship. We know that this is going to represent a line going from spaceship to base, since those are 2 points. We can also figure out the direction of this. I'm going to call it the u vector, by just taking the difference of those 2 points. And now we want to look for every single asteroid. Does the path or does the line that that asteroid is going to take, would it intersect with this line? And this is hard. Of course, if this was just in 2D, it would be much easier. Because in 2D, all you have to check is you fix this point right here, you fix this one, and then you compare it to this one. From here, you know you have to do counterclockwise. Then over here, you have to do clockwise. Since you have to do those two different directions, you know this intersection.
Interesting.
Yeah. So that's one property for 2D. But for 3D, it's different. And it's a little bit harder. All right, I guess I can leave that up for a little bit. In 3D, there could not every line. Some lines, although they cross, they are still parallel. Doesn't mean there's intersection. For example, this right here, if you look at it from a 2D, they intersect. But in reality, since it's 3D, it doesn't. So we want to find the smallest distance between two lines. The segment between any two lines and that magnitude of that vector or that segment will be the smallest distance between those two lines. Let's see if I butchered that. I can give you guys an example. Let's see if there's another line going like this. Let's say this was an asteroid that started here and told us that its direction, called that V, is going that way. Here, the vector that represents this right here, called this PQ, for example. The magnitude of this vector can represent the shortest distance that these lines ever get to, like the closest they ever get in that 3D space. That's essentially what we're trying to find. Does anyone know why we care about closest distance of two lines instead of just whether they intersect or not?
Because if you can find the close distance and it equals 0, then they intersect.
Yeah, if it equals 0, we for sure know they intersect. But what if it equals 5? Are we always going to say that they would not collide?
If that's the closest distance, yes, they would not collide.
They would not collide? Does everyone agree with that?
But I think they didn't get that part of the problem.
Okay, so let's go over it again. I'm going to blame this on David because he said treat them as particles. So asteroids are not particles. Asteroids, they are absolutely huge. They do have dimensions. And from now you probably know why.
We have a center of mass.
Exactly.
Do we even know the shape of the asteroids, or are they spheres?
Let's get to that as well. You said they're particles. They're not particles.
No, I said the ship is a particle. The asteroids have dimensions.
Oh, you said the ship?
They have dimensions.
Yes.
Okay.
The asteroids have dimensions.
Okay. All right, I believe you. Okay, I believe you. So here's what we're given about asteroids.
We have the rotation.
Yeah, they rotate, yeah, as well. We do not know if it's a sphere, but we are given its convex hull. Does anyone know what a convex hull is?
Tightest area of the object.
Exactly. If you were to take a rubber band and stretch it around these points and then let go, it would take this form right here. So this convex hull could be irregular. It's not necessarily a sphere. So since they also told us they rotate at an unknown speed, how can we treat this asteroid? We could treat it as a sphere, exactly. And how are we going to construct this sphere?
Okay, we just get the diameter.
Diameter?
Well, if you want
Radius.
To play it safe, you could take the point that is the furthest from the center of mass and say that around that.
Exactly.
Is gonna,
And that's exactly what we're going to do.
That's the radius.
Yeah, that's why it's a radius, yeah. So although, since it's an irregular, we want to treat it as a sphere because since it rotates, we don't know. There's a possibility that it could hit the ship because it's rotating at a certain angle where it just touches the ship. And that's a collision. So we're going to treat it by, let's say this is the center of mass right here. Let's look at all of them, and the one that's farthest away, let's get that radius. I believe the farthest one here is this one. Let's take that radius and construct a sphere with that radius. Yeah?
No. I was just asking him if he would surrender, if that's the only thing. He has enough space, but he knows that there's just this one point that if he happens to be that unlucky, he's gonna die. Is he gonna surrender? Or is he gonna take the risk? Let's take that risk.
Yo, why don't we just take the risk?
All right, let's not take that risk. All right, so we want to construct a sphere from this farthest point. And now we can play safe. And now we want to ask ourselves is, for the line for this asteroid, the closest it gets, let's call that D, is D less than or equal to the radius of this sphere?
Very good,
If it is, what do we do?
If it's less than the radius, then that implies that you're going to collide with it.
Yep, if it's less than or equal to, we surrender. We know we will get hit by an asteroid, so let's not even try and die. What if it's greater than? What if the distance of these two line segments is greater than the radius of the
You're
sphere?
going to collide that through the asteroid.
Exactly. So might as well go through the asteroid belt and potentially live. Well, most likely live. Well, will live. Cool. So now we know exactly what we're getting ourselves into and what we're trying to find. Now you guys probably know that what we want to find is that little segment, that PQ that I had drawn there. Now I want to go over something else. If I had a line and a point, and also the direction of that point, does anyone know what we can do with this property right here? I know you guys know because you went over it. But just out of curiosity, do you guys know how we can pretty much choose any point on this line with just one point in its direction?
I mean, you probably you have velocity, you can factor in time to pick a point, essentially.
Say
I
it?
don't think I quite understand. So P is
Just a point on this line.
it's a point on this
Yeah.
line.
And then U is the direction of this line is going.
And when you say pick a point, what you're saying?
Okay, I guess I can write it out because yeah, it is pretty hard to explain. So if we start at the position vector, which is just 0. For this case, you can think of it as n zeros, with a 0 for every single one of your directions. Just think of it as the origin. If we were to draw a vector from 0 to p, call that the p vector. And then let's say we want to represent this point over here. Well, we can represent that point with this vector, q, and we can construct that vector q with p and u hat. So is equal to p plus lambda of the u vector. Does this make sense to everyone? I think someone told me that they got a little bit stuck or didn't, from this part on, they were a little bit confused. So, yeah.
What's lambda again?
Lambda is just any real number.
Okay.
Yeah. Yeah, it's a scalar, but yeah, it's represented with this. Yeah, it's a scalar. Yeah.
So essentially, you're transforming the vector P, Q to be you're transforming the vector P to be different vectors, right? Like to represent all the points in the line, and the way you
Exactly.
places you're using alpha as
Lambda.
Yeah, lambda in order to transform.
Exactly. So that lambda, with this p vector, we can stretch or augment this p vector any way we want by using lambda and the u vector, the direction vector. So if let's say I have a positive lambda, I'll be moving it over here. And I can represent any point on this line with just this. And if it's negative, I'll be going backwards. So that's how we can construct that q vector from just the p vector, which is from 0 to the point p on the line, plus a factor times the direction of that vector. That makes sense to everyone. I like to think of it just a rubber band, again, just holding it here. And with a positive lambda, I'm just stretching that rubber band to any point that stays on this line. It's strictly on this line. And then if I'm doing it backwards, it's a negative lambda. So this all makes sense to you guys? Cool. So as we already went over, our goal is to pick a line. If we have let's say we also have the line, this is our line right here, call this base. This is the asteroid. We want to choose a line that connects these two, and that line we choose has a special property, where the angle between this, call this PQ, The angle between PQ and the asteroid vector, or asteroid line, is be 90 degrees, and it's be the exact same case for PQ and base. Anyone want to explain that? Or why that makes sense? Huh?
You're saying that okay, so the line from where I'm seeing it, the line below is the line from the spaceship to the space.
Yeah. So this is, I can label this as well.
And then the other line.
This is just the asteroid, yeah.
Asteroids, okay.
And then this line
The distance is going to be perpendicular.
is going to be the smallest distance. That smallest distance, if we were to do the dot product between this segment right here, with this vector and this line, we're going to get 0. And that tells us that there's a 90 degree. Why?
Oh, because when equals 1, cosine is 0.
When it equals 1, it's going to be 0, but will we ever want it to be equal to 1?
We want it to get to the base. But
Yeah, true, but we're trying to find the vector. Okay, so let's say this is my asteroid, right? And then this is my spaceship. I want to see how close they get. You want to help me? Oh yeah, never mind. Okay,
I get you.
they get this close, right?
Yes.
The angle that it forms between the top here is 90 degree, and the bottom is also 90 degree. Why?
Is that considered orthogonal? Is that what they're...
Yeah, you can. Yeah, it's orthogonal. Yeah, or normal. I think orthogonal means 90 degrees. Yeah.
Why it's 90 degrees?
Huh?
Why it is 90?
Yeah. Why is it always going to be 90?
Because that's the shortest. If it is more than
Exactly, because it's the shortest one. If it's not 90s, then that means it's tilted a little bit. You can think of it as taking the hypotenuse of a triangle. The hypotenuse is longer than one of the sides, so that's not the shortest. The shortest is always going to be 90. The shortest segment that connects these two, for each, the degree between each of the lines is always going to be 90, like I have right here.
And what's the significance of us verifying that, oh, I see, because you want them both to be, and that's when they are.
Since they're both 90, we know we can use some magic with the dot product, and we can somehow start working towards solving for this segment, for this vector, this PQ vector. And that's what we're doing next. Now that we know that property holds, we know what route we can go.
And then the magnitude of that PQ vector is the distance,
Yeah,
which is a scalar quantity.
it's scalar. So if it doesn't have direction, scalar, yeah. So now we can actually jump into solving the problem. Everyone's good, right? No questions? Right? Thumbs up, okay. Head nod, all right. All right, we're actually going to be getting to the math now, so this will be pretty fun. So we are given 2 points. And the direction of those 2 points. What does this tell us? It tells us that we have 2 lines. If we only have 1 point, right? If we know the direction of that 1 point, we know what line it's going to form. Oof, that was really bad, actually. This is the first point they gave us. Let's call that A. The second point they gave us is called that B. This U vectors represent the direction of that point A, and it's going in this direction. The next direction is called the V vector, and it's going in that direction. We want to find the point P and the point Q That's going to give us that property that we just discussed about, where if we were to take the dot product between this vector right here and then the vector from P to Q, we will get 90. We will get 90. So how can we find that?
My first idea is basically take two of the directions and see in that context where they intersect and do the same thing for another pair of directions.
So the direction is going to for sure help us out, but it's a little bit different from that.
Okay.
So let's say we have our 0 or origin right here. We're going to want to draw a vector from the origin to P and then from the origin to Q.
Okay.
Why do we want to do that? Because if we have these two, did I name them anything? Oh yes, this is P, and this is Q. If we have these two, then we can figure out the P to Q. Now if you guys remember, the P vector is going to be equal to A plus lambda times the U vector. Then the Q vector is going to be B plus mu times the V vector. Any confusion so far? This right here is exactly what we went over previously with those two lines. Is that confusing anyone? I think another way you guys can look at it as well, in case the whole PQ is confusing you, is this is our origin, and we know P, right? Let's assume we know the line the P sits on. If we assume its line, then using P hat, we can then figure out, sorry, not P hat, the P vector, we can then figure out the Q vector. Let's assume something like that, right? Which is why we're bringing back this property that we previously saw when we were just studying one line. You guys okay with this, or is there any confusion? I know it's a lot to digest, but just let me know. I can explain it, hopefully. You're good? This part makes sense why we're doing this?
Yeah, it's essentially the same thing. You're trying to be able to represent every single point on each of those vectors using O as the origin and then drawing two lines.
Exactly. And we want exactly this point where that's on the other line. Exactly, yeah. Cool. You guys are good? Good?
I get it, yeah.
Okay, cool. All right. So this is pretty much it. The real issue, of course, is now for solving for our unknowns, which is lambda and mu. They could be the same, they could be different, but they're just something that we do not know. And our goal is to find their value. If we find their value, then we can find this vector right here. And we know how close they are. Keep this in mind or write it down on your notebooks, because we're going to be going over an example and it's going to be using this right now. I can erase it, right?
We know P and Q, right?
P and Q we do not know.
We don't.
Yeah.
That's why you calculated using.
Exactly. Exactly. Exactly.
Yeah.
Okay.
But we do know A, we do know B.
We know A, B, U vector, and the V vector. Exactly. All right, I'm going to go ahead and erase this now.
So say that Q is equal to B plus lambda vector.
Plus mu V vector.
Oh, mu.
Yeah. Yeah. I'll erase this first in case you're still writing that. Okay. So now let's do an example. I'm going to be giving you the points A, B, the direction of A is going to be 1, 1, 1. All right. So anyone wants to remind me what P is equal to? David, how about you? What is P, the P vector, equal to? I know you were paying attention.
I mean, yeah, of course I was. I know exactly.
He knows exactly what it is.
I don't know what it is.
Wait, I'll tell you Q. I'll ask you for Q. I just want to call out on David for looking at his laptop.
No, it's my. Oh, actually, yeah. Okay. P is A plus lambda U.
And he's 100% correct. A true genius we have right here.
And I wrote it down.
Goodwill Hunting right here.
So,
All right, Alex, you want to give me Q?
Yeah, it's B plus mu times the vector, which is B, I guess, in this case.
Exactly. Cool. So we can actually plug things in now. Let's see. Let's evaluate what P hat, or sorry, I keep on saying P hat. What the P vector is equal to. Demba, go ahead and tell me that.
The P vector is equal to point A plus, what is that? It's not alpha, right? It's
Lambda.
lambda, okay.
Yeah.
The vector.
The vector, which is 0. What is this going to evaluate to?
This, I don't know.
No? Okay, it's fine, it's fine. So lambda, let's distribute it to all these elements right here. Lambda times 0 is 0. 0 plus 0 is going to be 0. Lambda times 1 is 1. 0 plus lambda. Sorry, lambda times 1 is lambda. 0 plus lambda is just lambda. Lambda times 1 is lambda. Lambda plus 2 is going to be lambda plus 2. I'll go over that because I kind of feel like I did that too quickly. So distribute all the lambda to all of these. And then the first one, you add them. The second ones, you add. And the thirds, you add. That makes sense? Cool. All right, I'm sorry, I don't know, what's your name?
Nikon. Go ahead, Nick, it's easier.
Nick? Okay.
Yeah.
You want to give me Q?
Yeah, and I was just doing it now. It's going to be Q with equal, essentially B plus mu, was it mu?
Yeah.
B, yeah, plus mu D.
And do you know what that evaluates to?
That's going to come out to 1,
Yeah.
and then 1 plus mu,
Uh-huh.
and 2 mu minus 1, or how are we going with that?
Yeah, exactly. Cool. So that's exactly right. It's the exact same process as we did for P, but now we're doing it for using the B point and the V vector. All right, let's see if you guys remember this one. We show up B vectors. We're doing it like this. Anyone remembers?
You're just going to take Q minus P, essentially.
Exactly. Q minus P. Alex, you want to tell me what this evaluates to? If not, it's fine. I can give it to someone else.
Yeah.
Okay. Demba?
The first one would be 0. Second
One.
one
Wait, what?
1 would it be?
Yeah, it'll be 1.
It'd be 1.
1 minus 0?
Oh yeah, that's 1.
Actually, I could do it. I just didn't see the problem.
Okay, give me the second one then, the second element.
That should be mu plus 1 minus lambda.
Yeah. I'm going to write it as mu minus lambda plus 1. David, give me the third.
2 mu minus 1 minus lambda minus 2, so that is 2 mu minus lambda minus 3.
Bingo. Nice. I'm telling you, this guy's a genius, bro. All right, cool. Now what? Let's see if anyone remembers. I did say it, but with this information, I'll draw it to give you guys a little hint.
Product with the
Yeah.
Or the
With the vectors.
vectors, yes.
With the vectors, exactly. We have essentially solved for PQ, which is this right here. Remember, this is our B, this is our A. U is going that way, B is going this way. Wow, there's a lot going on in this board. We essentially just solved for PQ, which is this vector right here. And now we need to confirm that this is a 90-degree. And how can we confirm that? By using the dot product between this vector and the U vector. So essentially, PQ, that vector, dot product of the U vector should equal 0. And that 0 should equal PQ times the V vector. Because they should be forming that 90-degree. So we need to solve, and this is how we're going to be finding what lambda and mu is, by solving for this. This makes sense to everyone?
This property holds due to the cosine of 90, right?
Sorry?
The cosine of 90. Well, why does this property hold? Because that product is multiplied by the cosine of 90, which is 0.
Exactly, which is 0. And that cosine 90 is will be telling us that this PQ vector is going to be normal to the U vector, or orthogonal. So it's be telling us straight like that. And if it's 90 in one vector and 90 in the other, then we know that's the closest distance, and that's the shortest from one vector to the other. All right, I might erase a lot because the rest is just math and plugging things in, which could take up a lot of real estate. We're all good with this? I can erase it, or you guys still writing it down? Erase it, okay. I'll start from the top. All right, so what I'm going to write back is PQs, because we did some pretty hard work to figure that out. Let's not make that go to waste. By the way, sometimes you might be seeing me write it like this or like this. It's the same thing. Since it's a vector, it should be written like that. But I'm just probably going to be doing this because I'm lazy. All right, cool. So PQ is equal to 1 mu minus crap. This is so ugly. There we go. All right. Let's solve the first one. First one was PQ times U. That should equal 0. If we were to expand this, what would it be? The dot product.
It would be the U vector times the PQ vector equals 0. Like it would be the formula of the dot product.
Isn't it cosine, like those two component vectors times cosine theta?
So close. You guys are saying this one?
Okay, but that's not expanding it.
Yeah, exactly.
Yeah, that's not expanding.
There was another one,
Would it be the formula, the long one?
the long one. It's exactly. We're going to want to do the long one,
Yeah.
which is going to be 1 times a U vector. Oh, I also have to write down the U vector. Very cool. I did transpose so I can write it in a row and not as a column. Trying to use as little space as possible. So this is going to be, let's just plug everything in. Or not exactly, yeah, let's substitute everything in. That's a better term. It's the correct term. let's have Demba tell me the first part.
The first part.
Yeah.
The multiplication.
Yeah.
X1 times x2, which is 1 times 0 is 0.
All right, you got it right this time. We don't talk about that.
What we're talking about this time?
David, you give me the second one now. Second element times the second element. Don't look back at your notes. It's just multiplication. It's this times 1. What is it going to be?
Oh, is that?
Just that? Which is, what is just that?
Mu minus lambda plus 1.
There we go. Cool. All right, Nick, you want to give me the second one?
The third one.
Yeah, third one, sorry.
2 mu minus lambda minus square. That's your first component.
Cool. Now let's also do the exact same thing for PQ times V, or dot product V. I'm not going to write it out. Let's see if you guys can do it in your head. Demba, you want to give it to me? Actually, not Demba. It's the same thing. Demba, give me the second one. The first one is 0, so just give me the second one.
The first one 0, the second one.
Yeah, because this is 0.
Two vectors, the v, and then it's gonna be the same thing. Because
Yeah,
this one-
it'd be the exact same thing as we have down here. David, give me the third. Wait, Alex, you want to give me the third?
No.
No? Are you sure?
No.
Please,
Okay.
please do the third, please.
Sorry, just trying to take down. Let me see.
This one's V.
So it's going to be this right here
PQ.
times 2.
So third component times third component.
Yeah.
Oh, right. Third. So it'll be 2 times. So it'll be 4 mu. Is that what it is?
Yeah.
4 mu minus. Was that lambda?
Yeah.
2 lambda minus 3 minus 6.
Yeah, there we go. Cool, so now we know what they're both equal to. How can we solve for this? We have 2 unknowns. How can we solve 2 unknowns in this system? There's multiple ways of doing it. Hopefully you guys say the way I do it. You okay, Demba?
No, I'm just thinking like the p times v, the last one, that's 2 times 2, which is 4 mu, right?
Yeah.
And then, oh, that's lambda, it's not 4.
Yeah, that's a lambda.
Okay,
Yeah,
so
yeah.
it's 2 lambda.
Yeah, my bad. All right.
Basically scale and cancel out like one of them at a time.
So you did it the way the Giri did it, which is the way I don't do it. But it's fine. You can bring this over here. You can like bring in the bottom. And yeah, you multiply this by like some value, you multiply the other one by the other value, and eventually all the lambdas or all the mu's will cancel out, and you know what one unknown is equal to. And then with that information, you can figure out the other unknown. Let's do it the other way, please. Because that's the only way I actually know how to do it. And it's the longer way, so it's not as efficient. But it's okay. Basically, just bring everything to one side. And have lambda equal to something, or or mu equal to something. So it's just basic algebra from there, to be honest. We could do some work here though. Wait, did you say something? Did someone say something?
No, I said
No.
it's good.
Okay.
You just replace the value of something arbitrary.
Yeah, exactly. So I'm going to choose lambda. Let's solve for lambda. So we have -2. Lambda is equal to -3 mu plus 2. Lambda is equal to 3/2 of mu minus 1. Right? Everyone good with that? Yeah? Okay. Okay. Yeah, it works out. Just trust me. It is correct. Now, we can also do some work here, actually. There we go. We made them a little bit nicer. Now let's just take this lambda and plug it right into here. So we have 5. I think this was the correct way of doing this. All right, anyone want to do some quick maths before I'm able to write it out? Ooh, this is off. This might be off. No? +1? Wait, let's just see. This is definitely off. Okay.
How'd you go from lambda to 5 mu? I think you put mu twice. Oh, are you going down from on the right side? So, 4th line from the bottom on the right. Yeah, where'd you get that from?
I plugged in lambda.
Okay, never mind. Okay,
That should be
okay.
plus the 5 mu. You should have plus because it's, oh no, it's minus because okay, it's
Oh, it's here. I think the issue's here. Oh, this is wrong. -3. This is minus. Yeah, no, that should have been minus. I had plus here. That should have been minus. So now it's 3. Okay, this is fine. We found the bug. All right, cool. So now let's just continue as normal, as nothing ever happened. And that's correct. Cool. Long way. You're taking your SATs, don't do it this way. You'll be wasting a lot of time. Thankfully, I'm not. Now we know what mu is equal to. We can go back here. Lambda is not equal to 3/2. 4 minus 1. Anyone?
That's going to be 12 over 2 minus 1. So 12 over 2 would be, wait.
Yep, got it. 5. Yeah, 12 over 2, 6 minus 1, 5. That was intense. You guys are practicing for the competition. We're doing some maths. All right, so we have the information. Anyone knows what this means? I erased it, but if you guys remember.
This means that now we can go back and substitute for point P.
Bingo.
Yeah, we can calculate PQ now.
Exactly. So I'm going to give myself some more space. I'm going to erase this. I'm just going to erase all of this top half. If you guys remember, P is equal to, where is it at? Here we go. Q is equal to, with our information, we can now plug it in. I know I erased what A was equal to. You know what? I'll write right here. A is equal to 0, 0, 2, 1, 1, negative 1. Cool. So if I were to plug it in, anyone? See if you guys can do it in your head. If you can do all of this in your head. Little mental challenge. Just start here, then just add. And that's what I recommend. And remember that lambda is 5, mu is 4.
So it's going to be 0, 5, 7.
Yep.
Yep, he's right.
What's the other one?
I mean, 1, comma, 4 minus
1, 4, 3.
1, 4, 3. Close.
It's gonna be the second point in Q is what? Oh no, wait, sorry.
1, 4, 2. No.
5. He got it. Demba got it.
Yeah, it is 1.2.
Not 1, 5, 2. It's the third one is not 2. It's something else.
Oh, please.
The type one is gonna be 4.
7.
7. He got it. Nice.
Sorry, I'm just like looking at the formulas in my notes and it's just a whole word.
Oh my god, I was looking at you still.
You're looking at you. Yeah.
I'm looking at you.
Yeah. Yeah. That one's going to be mu times v. All right. So with that information, we can go back to PQ. And I'll just write it out here. It was 1 mu minus lambda plus 1, 2 mu minus lambda minus 3. What would that be equal to? Obviously, we know there's a 1. I'll give you a hint. It's really simple.
I missed the question.
Oh, yeah. What is PQ? So now you just plug in the lambdas and the mu's. Huh?
0.
Which one?
The second one, the
Uh-huh.
second value will be 0, right? Because
What's the third value?
3 minus 5 minus 3 minus 0 as well.
It will also be 0.
That's the vector PQ.
This is the vector PQ, exactly. So this is this vector right here. Distance is just 1 in the x plane for this case. Is that accurate? Well, we can just check. Let's look at what P is. Let's look at what Q is. There's only one difference of 1. Therefore, we know for sure that's correct.
Why do we care about the point PQ?
Because it's this vector right here.
No, like why do we care about the point? Because we could have gotten the vector without solving for the points P and Q.
What vector are you talking about?
We could have gotten the vector PQ without.
Oh, yes. You're talking about these two separate points. We don't really care about them. Yeah, well, we use them to get what PQ is, and then we solve for PQ. But we just plugged it back in just to verify. And you can see how, since remember PQ is just to be the difference of P and Q, so you can just look at them as well to get.
Like other way to verify.
Exactly. So there's two ways. Either just plug it right here, or plug it back into your P and Q, and then subtract them, and it should match up. In this case, it does. Because if you're going to do PQ, it's going to be 5 minus 5, 0, 7 minus 7, 0, 1 minus 0, 1. And that's the distance. The magnitude of this, 1. So if our asteroid has a radius that is greater than or equal to 1, let's surrender. We will crash and we will die.
Can we do like a quick recap of everything? Like just like one.
Can I resolve this?
No, not resolve. It's like I
Yeah, no, I know. But can I erase it? Wait, Alex, you said not yet?
No.
Oh.
It's fine. I'm fine. I was just wondering why it was the magnitude PQ was 1, and I realized I looking at the square. Yeah, square root of 1 is 1.
Exactly, yeah. Square root of 1 squared, it's just going to be 1 because everything else is just 0. So,
Right.
yeah. All right, I'm going to erase it and I'm going to do the recap, or a quick recap. Also, just a little hint, you can't really solve the programming problem this way. because it's pretty hard. How would you do this? How would you code something to do this?
Wouldn't there be like some code already out there for solving these types of
There is, but the formula is for the distance is actually this.
I mean, I'm not too familiar with like the competition, but can you use like math libraries or no?
Yeah, I think some like the standard math library for sure could use. I can't verify NumPy. I don't know about that. Probably not PyTorch. You can't create a model to solve this. So yeah. But if you go online, this is a distance formula they give you, which is much easier, where n is e of 1 cross product e of 2, and where e1 is direction of point 1. You know what, just to make my life a little bit easier, e of I is the direction of point I. And there's only 2 points, so it's be e of 1 and e of 2. I just don't want to write it again. If you go online, that's what you get. But what we did is a little bit different. I guess that's okay.
Then what's R1?
R1 is R2 is just the points. The point of the spaceship, point of the asteroid. Yeah.
Wait, what's N again?
N is just the cross product of the direction of those 2 points.
And D is supposed to be for the like
Distance.
distance.
The closest those two lines get, those two vectors.
Those 2 points of R1 and R2.
Cross product of the direction of those 2 points.
Oh, they're vectors.
Yeah, yeah.
Got it.
Okay, so cross product of the vectors of both vectors, right?
Sorry, say it again?
Cross product of both vectors
Yeah.
times R1 minus R2, which gives you the distance, which gives you like a straight line, the vector of the asteroid divided by whatever n was. Is
Right.
that like the absolute value of n or?
Magnitude, because N is a vector.
I think it's like they call them like asteroids. Really, it's just like huge. If you're like visualize it, it's just huge cylinders that
The-
are just like floating and blocking your path.
It's exactly that, yeah. You can think huge cylinders with hemispheres on both ends.
Well, there's no hemispheres because there's no. Well,
If it
no-
starts, right, it can start in a direction. So in the beginning is a circle, a sphere. Then you're moving that sphere through space. So yeah.
Very good. Yeah.
Wow. So why didn't you just start off with this, man?
I know. So if you try to do that, it's still not going to be right.
Wait,
There's still some things you have to,
cylinder with 2 hemispheres?
yeah.
So,
So if you start off,
isn't that just a sphere?
if you start off with a sphere,
Like a pill shape. It's a big
Right.
pill shape, a long pill.
Right.
let's say I now move that sphere through time or through distance.
Oh, I see, I get it. Oh, so it's
Yeah.
all on these and
Yeah, on the ends, yeah. At the caps.
I mean,
not
but
the.
if
No.
it's infinite, it's like
If it's,
it almost doesn't matter.
yeah, if it's infinite, you only have one hemisphere.
On this sphere on this side. It's on this side.
All right, so I now encourage you guys to look over what we did today. Look more into it and try to solve the problem. The problem is hard. Computational geometry is a difficult concept. If you see computational geometry during any competition, it's a good chance that's the hardest problem. But either way, this one was actually not that hard. Like in terms of like someone who's highly competitive, this is trivial. There's that word again. This is trivial to them. But this is for sure still a challenge. At least in my opinion, I do still think it's hard. But yeah, try to code it out. You might have to do some research. There are some, I really don't know how to code what we went over today. That's what Giri showed us, but I have no idea how to write that as a program.
You should probably find some stuff that solves those equations for the contest.
So my initial guess was to make it as like a system of linear equations and solve that system of linear equations. So just linear algebra, maybe you could use linear algebra package, or you could just do algorithms.
Solve it like that, using like some sort of like a matrix multiplication.
Sure. Well, to solve system of linear equations, it's either you need to make it strictly triangular and then use back substitution, or use Gauss-Jordan reduction, or reduce echelon form. There's multiple things you can do to it. But yeah. But they're all algorithms that can be done. It's just difficult. So I can't do the recap, by the way, unless you want to stay after.
No, I think I get it.
You think you got it? Good.
Yeah, the 2 points we do come up with is to follow the representation point of it, right?
Yep.
With vector. Multiply that vector with u and v. So for it because of the
Because of the unknowns.
product.
Yeah.
And then after you do that, then now you get the vector of p of random minus stuff.
Yeah. All right, so other than that, I want to thank you guys for coming. Hopefully you enjoyed. Hopefully this was a fun problem for you. And if you're competing, good luck. Hopefully see you guys in next week's lecture. Thanks.